Okay, let's get into it. We just have a few more cases of planar phase portraits to consider. We've done the cases when you have real distinct eigenvalues, and we considered the cases when they were either positive, negative, or zero, and with same or opposite signs. So the cases that are remaining are the complex eigenvalues and the real repeated eigenvalues. We know from complex eigenvalues that they will always come in complex conjugate pairs, and the eigenvectors will also come in complex conjugate pairs, and a typical solution looks like this. X equals e to the alpha t cos beta t a minus sine beta t b. That's not the general solution, that's just one solution. But as we'll see, once if you can graph this one, then you've got the general phase portrait already. So the question is, what is the graph of this equation look like in the plane? First I'll do the case alpha equals 0, because then this factor out in front is just always equal to 1. Now these coefficient functions, cos beta t and sine beta t, these are periodic, and the period that they repeat is 2 pi over beta, because when t is equal to 2 pi over beta, the argument is 2 pi, and that's the period of sine and cosine. So the whole solution will repeat every time 2 pi over beta. If beta is very large, the period is very small, and the solution is oscillating very, very fast, very high frequency. So here we go. What's it going to look like? When t is equal to 0, cosine of 0 is 1, and sine of 0 is 0. That means I'm just at the point A, so let's suppose vector A is in this direction. There is vector A, and this will be t equals 0. Where am I after a quarter period? That'll be t equals a quarter of 2 pi over beta, so that the arguments of these sines and cosines are pi over 2. Well, cosine of pi over 2 is 0, sine of pi over 2 is 1, so I'll be pointing in the direction minus b. So let's suppose b is here. I'll be in the direction minus b at t equals a quarter 2 pi over beta. When t is a half a period, a half times 2 pi over beta, then beta times t would be equal to pi. Cosine of pi is minus 1, sine of pi is 0. I'll be pointing in the direction minus a. And when t is 3/4 of 2 pi over beta, I'll be pointing in the direction b. Drawing those all up, and the solution is going to trace out an ellipse. Put a few more little arrows on it. And once I've gone all the way around, I'm back where I started, and then it will go around and around forever. So I have drawn the parametric form of one of these equations, and the precise ellipse that you get will depend on a and b. They will be the semi-major axes of that ellipse. What about the other solutions? Well, if I take a linear multiple of this, say 2 times this or a half times this, I'll just get scaled ellipses, so I can draw another one in like this. So I get a whole family of concentric ellipses. If I take the other solution that I haven't written down, it turns out, well, there's obviously no room for a different solution. All that is just a phase shift. So it's just the same solution, but starting a little bit further around. So there we go. When alpha is 0, I have pure imaginary eigenvalues. All my orbits, except for the fixed point at the origin, are ellipses. They're all periodic with the same period and just different amplitudes. This is called a center. And it is in fact stable. It's stable in a slightly more subtle way. If I start nearby the 0 solution, I don't actually return to it. And I may indeed move a little bit away, but I can't move arbitrarily far away. I'll just oscillate around it. That is still a stable fixed point. Okay, that was the case alpha equals 0. Now I want to do the same thing when alpha is positive, I think that's I'm doing negative first. When alpha is negative, all of that argument I did with the a's and the b's and the periods and so on, that will all be the same. It's just that as t increases, as I move around the ellipse, I'm scaled by e to the alpha t. And if alpha is negative, that factor is going to be getting smaller and smaller. That means, I'll do the schematic of the same solution again. If A was here and B was here, by the time I've gone around one period, I've shrunk by a factor e to the alpha t, where t is the period. When I go around, I've shrunk more, and I get a spiral. And in fact, I'm done now. You only really need to draw one solution, and that tells you what all the others are going to do. They're all going to be spirals that all nest in together. That is called a stable spiral sink. Could put a few more little more arrows on there. Everything spirals around, it oscillates, and it tends to the fixed point. And when alpha is positive, it's going to be an unstable spiral source. It oscillates and moves away. Okay. What case is left? There's the repeated eigenvalue case, and here there's still two cases, because if you have a planar system with a repeated real eigenvalue, there are two cases to consider. It may have one or two-dimensional eigenspace, and the phase portraits will look different in those two cases. So here's an example of a system with a repeated eigenvalue. It's -1 and -1. And in this case, I've just got one eigenvector. There it is there, one eigenvector 1, 2. So from this solution, how do I graph these curves for the general solution? Well, let's think about it. I can graph that solution when C1 is 0, and then I'll always be pointing in the direction 1, 2. That one is easy. Which way do my arrows go? As t increases, I tend to 0. Must tend to 0. So that's the C1 equals 0 case. That's easy. What about the other solutions? So there's no second eigenvector. So what I want to do is take an arbitrary solution, so arbitrary values of C1 and C2, and consider what happens as t tends to plus or minus infinity. And you notice that because all the e to the minus t parts are all tending to 0 at the same rate, but this one is multiplied by t. As t tends to infinity, I'll be pointing in the direction 1, 2. And as t tends to minus, this will be the dominant term, much bigger than the other ones. And as t tends to minus infinity, I'll be still in the direction 1, 2, but now with a minus sign in front. So that means I have to always be tending to this direction 1, 2, but either in the plus or minus direction. So it must look like this. So these solutions here, as t goes along, I tend to the direction 1, 2 from this way, and as t tends to minus infinity, I have to swing around and point to the direction 1, 2 in the opposite direction. And the other solutions that I haven't drawn yet will fit in this way. That arrow should go this way. So that is also a type of a stable sink. And that means the final remaining case is when I have a repeated eigenvalue with two-dimensional eigenspace. This time I've got lambda equals 1 and 1. Now my general solution looks like this. And I see that for any fixed values of C1 and C2, I'm always pointing in the same direction. So my phase portraits I'm either at 0 or I'm moving away along a ray, and the ray can point in any direction. So I don't now have a preferred direction like I had before. I can move in any direction. That is a stable source. Now, it seems like a lot of cases to consider. We've gone through them all now. But the great thing is this applies much more than just to planar linear systems. First off, it applies to linear systems in any dimension. You can't draw the phase portrait so easily, but these building blocks do tell you what all the phase portraits can look like for any linear system in any dimension, so that's pretty important. And we'll see later on that they also tell you what phase portraits look like for nonlinear systems close to fixed points. And that's a very important conclusion that we're going to be getting to fairly soon. Kia ora.